So a Riemann problem, even though it's called the Riemann problem, it really is a family of problems. A family of problems that for any equation, which could be, for example, the 1D Euler equation, the Riemann problem has, well, it has two components. You need a conservation law, like the Euler equations, plus a particular type of initial data, which is piecewise constant. Piecewise constant, but with a single jump discontinuity. So, for example, for the Euler equations, you could define an initial, well, we've done it already for the Burger's case. It's the same one, right? We just need to have a single jump at a particular point, like the assignment that you're supposed to be working on now. The velocity at time 0, let's just call it t0, has two sides. It takes one value, say u left, with x less than x0, and u right with x greater than x0. And in this case of the Euler equations, u represents the full vector of independent variables, right? It's analogous to the case of the Burger's equation, where you just have a jump in u, but now this u vector includes all of our conserved quantities for the Euler equations. So UL and UR, of course, are just constant vectors. For convenience, we can take T0 equals just 0, or we could take for example, for convenience. And it turns out that with this initial data, this Riemann problem has an exact analytical solution for the Euler equations, which is very useful, because if we have an analytical solution, which is very rare for these nonlinear partial differential equations, it means that we can use it to test numerical methods and see how they perform. This is one of the uses of the Riemann problem. There are many other uses. It actually shows up in quite a lot of context, but one of the great uses of it is to test numerical methods, because it has an exact analytical solution. For the Euler equations. In fact, for any type of similar sort of conservation laws, scalar conservation laws, or any linear system of equations, linear system of partial differential equations. There are many features of the Riemann problem. I'm just going to sort of mention some of these features, because we can make reference to them afterwards when we use this Riemann problem to test our Euler solvers that we're going to write. So basically all of these steps that you're going to do for the Burger's equation with these schemes that you're going to try out, then in the next assignment you're going to use them again, but for the Euler system. You can see what's coming. So some of the features of the Riemann solver. One of the features is that the solution is self-similar. What does that mean? I'll say in a moment. Basically, it means that the solution stretches uniformly in space and time, but it doesn't change shape. So as time moves on, the solution might stretch in one direction, for example, but the shape doesn't change. The general shape, the form of the solution. Space and time. But does not change shape. So any two solutions at different times are similar to each other. So say u at, so this is a vector at a given point, and t1 and at t2 are similar in shape to each other. Or in other words, another way to say this is that it only depends on a single variable. The solution really depends on a single variable x over t, rather than x and t separately. Or another way to say it is also that the solution is constant along a line called the characteristic line, x equals c times t, with c constant on the xt plane. And this is sort of general for all self-similar solutions that you can, in this case, it's x over t. But in general, self-similarity has this feature that we have a single, only one independent variable which could be, in this case, it's x over t, but it could be in this case it's x over t, or it could be x over square root of, or t, or it could be t over square root of x. This is typical in boundary layers, or it doesn't matter. Some combination of the two independent variables. If you combine them in a certain way, you can basically do a change of variable, say call eta equals t over square root of x, and you can do a change of variables in your system, and it becomes a system of one variable. This is what it means to stretch a space and time. I can make a change of variable, and it will always look the same in this new system, reference system. So this is actually very useful, and it's used quite a lot. It appears in fluid mechanics quite a bit, boundary layer theory, and many other topics where you can use a similarity variable. Perhaps you might recall the Blasius solution of boundary layers from fluids, where you can obtain a solution in closed form. It allows you to get analytical solutions, and things simplify quite a bit, so this is quite useful. And the Riemann problem is one of those situations where you have a self-similar solution And so in this case, the similarity variable is just x over t. It's characteristic. So the other important feature is that because we have an analytical solution for the Riemann problem, then it's very useful to test numerical methods. It is, in fact, one of the very few exact solutions of the Euler equations. And another aspect of it is that it, in fact, the Riemann problem itself appears as an integral part of some numerical methods. It's incorporated. It appears as part of the formulation in some schemes in CFD. And that means that some CFD methods will require you to solve Riemann problems a large amount of times, and so that means that doing this efficiently becomes really the crucial part of the heart of the method. This is, in general, when you have situations with shock. They are used to provide, for example, what's called weight capturing methods. Many particular methods that have been designed for compressible CFD require you to solve Riemann. You require Riemann solvers. They're called at the heart of the method. And you might have to solve Riemann problems millions of times within a particular solution. So it becomes really the most important cost of the CFD solution is the Riemann solver. And so there's a huge amount of literature and research that has gone into solving Riemann problems in an efficient way. So it's a very important branch of CFD. There's actually books, whole books written on this, Riemann problems, Riemann solvers, okay? So we're just going to scratch the surface of this by knowing what it is and doing a classic test, Riemann problem type test for the Euler equations. Okay. So this is the classic test we're going to do. It's called the shock tube problem, and it's basically the following: you consider a 1D tube, a one-dimensional tube. So I'm going to draw this tube. It's infinite, but I'm just going to draw a little piece of it. And inside this tube, you consider that at time equals 0, you're going to have two regions of fluid which are separated by a membrane, a diaphragm, that is just sitting there. And you have a pressure here, P1, assumed to be high or higher than the pressure on this other side that we're going to call P5. This is a 1D tube. It's also infinite in linear dimension. This is the assumption. And the flow is going to be inviscid. These are the conditions. So the idea is you have this situation at time equals 0. And at this point, the diaphragm is instantaneously removed In fact, this is done experimentally. The shock tubes have some sort of very thin sheet of metal, and they're, with a small explosion, they're burst so that you have an experimental approximation to this problem. And so suppose that at time equals 0, then this diaphragm is instantaneously removed. And this, because of the pressure imbalance between the two sides, causes immediately a one-dimensional unsteady flow consisting of a steadily moving shock. So you're going to get a one-dimensional unsteady flow in fact, what you're going to get is a situation where this is a Riemann problem, okay? We're going to have a one jump, and the situation here is uniform on either side. This is your initial condition, right? Pressure uniform here, velocity is 0 everywhere, and pressure is high here and low there. And then this is at time equals 0 what happens. So it's a Riemann problem, and the solution is therefore self-similar. The self-similar solution for this problem actually consists of 5 regions. That's why we call this guy 5. And if I draw a picture of these 5 regions, what you're going to have is a shock moving to the right. This guy is the shock. To the right of the shock you have region 5 with P5. Then to the left of the shock you have region 4. You're going to have also a region 1 over here, which is region 1 and 5 basically have the states which correspond to the left and right side of the initial states. Then you have what's called an expansion wave, or a rarefaction wave in region 2. And region 3 here and region 4 are separated by what's called a contact line. So regions 3 and 4 basically have steady states which are independent of x. So all of the conditions in region 3 are uniform, and also all the conditions in region 4 are uniform, but there's a difference between 3 and 4. Independent of x within the region. And region 2 has this x-dependent state, which is the expansion wave. The divided line between 3 and 4 is a contact discontinuity because it separates, so this contact line between 3 and 4, separates two fluids of different entropy, but the same pressure and same velocity. So it's really an invisible line. There's no, for example, you could have a line of two fluids where one fluid has dye and the other fluid has no dye whatsoever. So water, and one side of the water has dye. And if there's a separation between these two, the two fluids have different entropy, but they have the same pressure, same velocity. Of course, this is moving. This contact line is moving. So P3 equals to P4, U3 is equal to U4. Okay, now this problem has an exact solution. I will provide you with that exact solution, but we won't go into details in class in the interest of time. I will just give you this to read, and perhaps to make it easier, I'll even give you the little code to generate the exact solution, because what is important is that you're going to code numerical solutions of the Euler equations with the different schemes that we study, and then compare the numerical solution with the analytical solution for this shock 2 problem to see how the numerical schemes behave. So the next thing we're going to do is discretize the Euler equations with some of the schemes we know, and I'll show you what this is going to look like. This is going to be the next assignment, the shock 2 problem.